Imagine gazing up at the night sky, where every twinkling star is a sun, some with planets of their own. And yet, in all that vast cosmic ocean, we've barely dipped our toes into understanding its deepest secrets. Space, for all its grandeur, is a puzzle with pieces we're still scrambling to fit together. Think about this. We've mapped every corner of our own planet, sent robots to Mars, and peered back in time to the edges of the observable universe, and yet, some of the most fundamental questions about the cosmos remain wide open, taunting us with their mystery. What's out there in the void? Are we truly alone? And why does 95% of the universe seem to be made of something we can't even see? It's humbling, isn't it? For all our telescopes, probes, and brilliant minds, space still holds onto its enigmas like a vault locked tight. Some of these questions are so baffling, they've haunted scientists for decades, like dark energy, that invisible force tearing the universe apart faster than we can measure it. Or black holes, those cosmic monsters where the laws of physics as we know them simply break. And then there's the eerie silence in our search for extraterrestrial life. With billions of galaxies, each with billions of stars, why haven't we found so much as a microbial hello? That's exactly what we're diving into today. 30 of the most mind-bending, spine-tingling questions about space that science still can't answer. Some might keep you up at night, others might make you question everything you thought you knew about reality. But one thing's for sure, by the end of this journey, you'll see the universe not just as a blanket of stars, but as a living, breathing mystery daring us to keep searching. So buckle up, we're about to venture into the unknown, where even the questions themselves are wonders to behold. Here's a cosmic riddle for you. Imagine the entire universe is a grand play, but most of the actors are invisible. That's the bizarre reality of dark matter, this mysterious, unseen substance that makes up roughly 27% of everything in existence, yet we've never laid eyes on it, never touched it, never even directly detected it. So how do we know it's there at all? The answer lies in the universe's own choreography. Take galaxies, for example. They spin so fast that, by all rights, the stars on their outer edges should go flying off into space like kids flung from a merry-go-round. But they don't. Something invisible, something with gravity, is holding them together, acting like cosmic glue. That's dark matter silently shaping the cosmos from the shadows. Then there's the way light bends around galaxy clusters, warping like a funhouse mirror. Again, the math says there's far more mass there than what we can see. So what is it? Scientists have tossed around some wild theories. One leading idea involves weakly interacting massive particles, hypothetical particles that barely talk to normal matter except through gravity. Another candidate, actions, ghostly particles so light they could slip through you 1 trillion times a second without a trace. There are even whispers about primordial black holes, leftovers from the Big Bang lurking in the void. But after decades of hunting using detectors buried deep underground, telescopes scanning the skies, even atom-smashing experiments like the Large Hadron Collider, dark matter remains stubbornly out of reach. And here's the kicker: without it, our entire understanding of the universe falls apart. Dark matter's gravitational pull sculpted the cosmos as we know it, guiding galaxies into their shapes, weaving the cosmic web. If we solve this riddle, we might finally crack the code of how everything from the tiniest particle to the grandest galaxy fits together. Until then, it's the universe's most tantalizing vanishing act. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine pushing the cosmos apart faster and faster in a runaway expansion that defies logic. Picture this: you throw a ball into the air, and instead of slowing down and falling back, it rockets upward at an ever-increasing speed. That's essentially what our universe is doing, and no one knows why. The story of dark energy's discovery reads like a cosmic detective novel. In the late 1990s, astronomers studying distant supernova exploding stars that act as cosmic mile markers made a jaw-dropping realization. These stellar explosions were fainter than they should have been, meaning they were farther away than expected. The only explanation, the space between galaxies wasn't just expanding, the expansion was accelerating, as if some unseen force was pressing hard on the gas pedal. This revelation won the Nobel Prize and turned physics upside down. So what could dark energy be? One leading theory points to the vacuum of space itself. Quantum mechanics suggests that even empty space isn't truly empty, it's a seething foam of particles flickering in and out of existence. This zero-point energy might generate a repulsive force pushing everything apart. But here's the problem. When scientists calculate how strong this effect should be, the numbers are off by a laughable margin, around 120 orders of magnitude. That's like predicting a gentle breeze but getting a hurricane powerful enough to shred the universe. Another idea ties back to Einstein, who once proposed a cosmological constant, a built-in energy of space that could balance gravity. He later called it his greatest blunder, but now it's back in play as a possible dark energy candidate. Yet even this leaves gaps. Why does dark energy dominate now after billions of years of slower expansion? Is it changing over time, or could it be something even stranger like a new fundamental force or a flaw in Einstein's gravity equations? The stakes couldn't be higher. Dark energy makes up 68% of the universe's total energy budget, dwarfing everything else: stars, planets, even dark matter. If we don't crack its code, we're missing the majority of reality's recipe. Future telescopes like the Nancy Grace Roman Space Telescope aim to map its influence with unprecedented precision. Until then, dark energy remains the universe's greatest silent upheaval, a reminder that the cosmos is far weirder and more wondrous than we ever imagined. Consider the numbers for a moment. Our galaxy alone holds an estimated 100 billion stars, and each could host planets. With trillions of galaxies beyond ours, the statistical odds suggest life should be everywhere, a cosmic chorus of civilizations. So where is everyone? This is the heart of the Fermi Paradox, the unsettling contradiction between the high probability of extraterrestrial life and our utter lack of evidence for it. The search begins close to home, in places we once thought lifeless. Take Earth's extremophiles, organisms thriving in boiling hydrothermal vents, frozen Antarctic lakes, or even the radioactive wreckage of Chernobyl. If life can cling to existence in these brutal corners of our planet, why not on Mars' rusty plains, Europa's buried oceans, or the methane rivers of Titan? Every discovery of a hardy microbe expands the boundaries of where we might find our cosmic neighbors. Then there's the Goldilocks zone, the sweet spot around a star where temperatures allow liquid water. Astronomers have spotted thousands of exoplanets in these habitable regions, some eerily Earth-like. Kepler 452b, for instance, orbits its sun at just the right distance, with a year only 20 days longer than ours. But here's the twist: we've barely scratched the surface. Most of these worlds are so distant, our current tech can't sniff out signs of atmosphere, let alone radio signals or city lights. Which brings us to SETI, the decades-long effort to scan the skies for artificial signals. Imagine tuning a radio to static for 50 years, hoping to catch a whisper of hello. The silence is deafening, but perhaps we're listening wrong. Maybe advanced civilizations communicate with neutrino beams or quantum entanglement, technologies we can't yet detect. Or worse, what if they're deliberately hiding, watching us like a nature documentary until we pass some galactic IQ test? The possibilities spiral into the surreal. Could intelligent life be rare, snuffed out by cosmic disasters or self-destruction before achieving interstellar travel? Or are we simply the first, born into a young universe still waiting for others to awaken? The answer might rewrite not just science but our place in the story of everything. Until then, we keep searching, because in a universe this vast, the silence is the most haunting mystery of all. Picture the most extreme prison in the universe, a place where gravity wins so utterly, not even light can escape. That's a black hole, nature's ultimate cosmic vault. At its edge lies the event horizon, the point of no return. Cross it, and every law of physics you've ever known becomes meaningless. Time distorts like taffy. Space stretches into an infinite descent, and what awaits at the center? The singularity, a point of infinite density where matter is crushed smaller than an atom, where gravity becomes so intense it punctures the fabric of spacetime itself. But here's where things get truly bizarre. According to Einstein's equations, the singularity shouldn't exist. It's a place where math breaks down, where quantum mechanics and general relativity, the two pillars of modern physics, start screaming at each other in contradiction. This is the heart of the information paradox. When an object falls into a black hole, does it vanish forever? Quantum mechanics says no, information can't be destroyed. Yet black holes seem to erase it completely, like a cosmic shredder. Enter Stephen Hawking's revolutionary idea. Black holes aren't entirely black, they leak. Slowly, over eons, they emit what we now call Hawking radiation, a faint whisper of particles born from quantum fluctuations near the event horizon. This radiation carries energy away, causing the black hole to shrink and eventually evaporate. But here's the catch: Hawking radiation appears random, like static. If the black hole vanishes, where does the information about what fell in go? Does it return to the universe scrambled, or is it lost forever? Scientists are torn. Some propose holographic theories where information is smeared across the event horizon like a celestial USB drive. Others suggest firewalls, searing walls of energy that burn up anything crossing the horizon. There are even wild ideas about black holes birthing new universes where the information resurfaces in another reality entirely. Yet after decades of debate, no one knows for sure. Black holes force us to confront the limits of human knowledge. They're cosmic riddles wrapped in enigmas, laboratories where the rules we cherish shatter like glass. And until we uncover the quantum theory of gravity, the missing link between the tiny and the cosmic, these monstrous voids will keep guarding their secrets with absolute crushing defiance. We think we know how the story begins, with a bang. Not just any bang, but the Big Bang, an explosion of space and time itself that set the universe into motion 13.8 billion years ago. Picture all the energy, matter, and forces we see today compressed into a space smaller than a grain of sand, hotter than the core of any star. Then, in an instant, it erupted outward, expanding faster than the speed of light during a brief period called cosmic inflation. Within minutes, the first atoms formed. Over eons, galaxies coalesced from the swirling leftovers. But here's the unsettling truth: the Big Bang isn't the beginning. It's more like the first frame of a movie where someone tore out the opening scene. We can rewind the cosmic clock to a fraction of a second after the bang, but what happened before, or what triggered it, remains a mystery. The equations of general relativity simply break down at that point, leaving us staring into a primordial fog. Some theories try to pierce that fog. Cosmic inflation suggests the universe underwent exponential stretching in its first moments, smoothing out wrinkles and planting the seeds for galaxies. But what drove that inflation? Was it a quantum fluctuation, a collision of higher dimensional brains, or something even stranger? Then there's the cyclic model, which proposes an endless loop of universes, each ending in a big crunch that births the next bang. In this view, our universe might be one page in an infinite cosmic novel. And what about the ultimate question? Why is there something instead of nothing? Some physicists speculate about a multiverse where universes bubble up endlessly, each with different laws. Others ponder a quantum origin where the universe literally tunneled into existence from nothingness. But without a time machine or a theory that unites quantum mechanics and gravity, we're left guessing. The Big Bang isn't just a scientific theory, it's a mirror reflecting the limits of human curiosity. We've traced cosmic history back to its fiery infancy, yet the first whisper of existence still slips through our fingers. Every answer unravels new questions, reminding us that the universe's greatest story might be one we're only just learning to read. Every story has an ending, even the universe itself. But unlike a book with a final page, the cosmos has multiple possible finales written in the language of physics, each more dramatic than the last. The leading contender, the Big Freeze, a slow, quiet fade into oblivion. Picture a universe where dark energy keeps accelerating expansion, pushing galaxies apart until they're so distant their light can never reach us. Stars burn out, black holes evaporate, and space becomes a vast, empty graveyard near absolute zero. It's not fiery or violent, just an eternal, deepening chill where time itself may lose all meaning. But what if dark energy behaves differently? Some models suggest it could grow stronger over time, leading to the Big Rip, a cosmic apocalypse where expansion becomes so violent it tears apart everything. First, galaxies would be shredded, then solar systems, planets, and eventually atoms themselves, ripped to particles too small to measure. The universe would end not with a whimper but a scream. Then there's the Big Crunch, a mirror of the Big Bang where gravity finally overcomes dark energy's push. Galaxies would rush back together in a catastrophic collapse, temperatures soaring until all matter is compressed into a single, searing point. Some theories even suggest this could trigger a new Big Bang, starting the cycle anew, an infinite loop of creation and destruction. But here's the twist, which fate awaits us hinges entirely on dark energy's secrets. Is it truly constant, or does it evolve? Current data leans toward the Big Freeze, yet the margin of error leaves room for surprises. Future telescopes could tilt the scales, measuring dark energy's grip with unprecedented precision. Until then, the universe's ultimate destiny remains suspended between mathematics and mystery, a reminder that even in the grand finale, the cosmos keeps its deepest cards close. Here's how the universe played the ultimate magic trick on us. It made something out of nothing, or more accurately, it made everything out of what should have been nothing at all. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter particles that are identical to their ordinary counterparts but with opposite charges. When matter and antimatter meet, they annihilate each other in a burst of pure energy. So why didn't the universe cancel itself out in a blinding flash of mutual destruction? Why does anything, the stars, planets, or even us, exist at all? This is the matter-antimatter asymmetry problem, one of the most baffling gaps in our understanding of the cosmos. For every billion particles of matter created in the early universe, there were roughly 1,000,000,001, a tiny, almost imperceptible excess that somehow survived the annihilation. That slim margin is all that stands between existence and an empty void. To understand how this happened, we need to dive into the subatomic Wild West, where particles behave in ways that still defy intuition. The first clue lies in something called CP violation, a subtle crack in the mirror symmetry of the universe. Normally, if you flip a particle's charge C for charge conjugation and its spatial orientation P for parity, physics should behave the same way. But in 1964, scientists studying kaons, short-lived particles, found that antimatter versions of these particles decayed slightly differently than their matter counterparts. This tiny asymmetry, like a cosmic scale tipping by a fraction of a gram, hinted that nature might favor matter over antimatter. Later experiments with B mesons confirmed it. The universe has a subtle bias. But here's the catch: the amount of CP violation we've observed so far is nowhere near enough to explain the overwhelming dominance of matter today. It's like trying to fill an Olympic pool with a teaspoon. So where's the rest of the asymmetry hiding? Some theories point to neutrinos, those ghostly particles that barely interact with matter. If neutrinos are their own antiparticles, a possibility called Majorana particles, their odd behaviors could have tipped the scales further. Others suggest that the true imbalance happened in the seething chaos of the early universe, moments after the Big Bang, when exotic particles like hypothetical leptoquarks briefly existed and skewed the balance. The stakes couldn't be higher. If we solve this riddle, we're not just answering why we're here, we're peering into the fundamental rules that shaped reality itself. Experiments like the Large Hadron Collider are hunting for new sources of CP violation, while deep underground detectors watch for neutrinos that might hold the missing pieces. Until then, the universe keeps its oldest secret close: how it cheated annihilation by the slimmest of margins, leaving behind just enough matter to build galaxies, planets, and curious minds to wonder about it all. One moment, space is silent. The next, a blast of radio waves brighter than 1 billion suns erupts across the cosmos, then vanishes, lasting barely a millisecond. These are fast radio bursts, or FRB, some of the universe's most baffling and explosive enigmas. First discovered in 2007, these bursts pack more energy than our sun emits in 80 years, yet they're gone before our telescopes can blink. And the strangest part, most never repeat. It's like the universe is playing an interstellar game of whack-a-mole with signals we can't explain. So what are they? The leading suspect is magnetars, super-dense, highly magnetized neutron stars that spin like cosmic tops. Imagine a stellar corpse so powerful, its magnetic field could strip the data from your credit card from halfway across the solar system. When these monsters experience starquakes or magnetic snap, a sudden rearrangement of their ferocious fields, they might unleash FRBs as a kind of cosmic scream. In 2020, astronomers caught one red-handed, a magnetar in our own galaxy firing off a burst strikingly similar to those from deep space. Case closed. Not quite, because here's the twist: some FRBs do repeat, flickering on and off like a malfunctioning beacon. Others arrive with bizarre patterns, clustering in ways that don't fit the magnetar mold. Could these be colliding neutron stars, black holes swallowing pulsars, or cue the X-Files music artificial signals from advanced civilizations? The latter isn't as far-fetched as it sounds. In the 1970s, scientists proposed that alien megastructures might emit purposeful bursts to propel light sails across galaxies. While there's zero concrete evidence for ET, the sheer power and fleeting nature of FRBs leave the door cracked just enough for wild speculation. The real challenge is catching them in the act. Most FRBs are detected by chance, their fleeting signals stumbled upon by telescopes scanning vast swaths of sky. New tools like the CHIME array in Canada are changing the game, spotting dozens a month and even tracing a few back to their host galaxies, often young, turbulent regions ripe with stellar drama. Yet for every answer, new questions erupt. Why do some FRBs drip with lower frequency waves while others don't? Could they be cosmic lighthouses, marking wormholes or other exotic spacetime structures? One thing's certain: these bursts are more than intergalactic static. They're encrypted messages from the universe's most violent corners, written in a language we're still learning to decode. And with every flicker, they remind us that the cosmos thrives on chaos, and that some mysteries refuse to be solved without a fight. What if our universe isn't the only one? What if it's just a single bubble in an endless cosmic froth? One page in an infinite library of realities. This isn't science fiction, it's the multiverse theory, a radical idea gaining traction among physicists desperate to explain the eerie fine-tuning of our cosmos. Think about it: if the strength of gravity were slightly weaker, stars wouldn't ignite. If the cosmological constant were a fraction larger, galaxies couldn't form. It's as if the universe's dials were set precisely to allow life to exist. But why? The multiverse offers a startling answer. Maybe there are universes where those dials are set differently, and we just happen to be in the one where everything lines up perfectly. One version of this idea comes from cosmic inflation, the theory that our universe ballooned exponentially in its first moments. Some models suggest inflation never truly stops. Instead, it spawns countless bubble universes, each with its own laws of physics. Picture a pot of boiling water with bubbles constantly forming and drifting apart. In this view, our universe is one bubble among trillions, forever cut off from the others by the relentless expansion of space. Some bubbles might collapse instantly, while others could harbor alien physics universes where time runs backward, where dimensions crumple in on themselves, or where dark energy strangles galaxies before they're born. Then there's string theory's landscape, a dizzying mathematical terrain with 10 to the 500 possible configurations, each representing a unique universe with different constants and forces. In this scenario, the multiverse isn't just vast, it's infinite, with every conceivable reality playing out somewhere. Want a universe made entirely of spaghetti? Statistically, it's out there, but here's the catch: we have zero empirical proof. The boundaries of these other universes, if they exist, lie forever beyond our cosmic horizon, unreachable by any signal or probe. Critics argue this makes the multiverse untestable, more philosophy than science. Yet some researchers hunt for subtle clues, like gravitational imprints left by a colliding bubble universe in the cosmic microwave background, or anomalies in the distribution of galaxies. Others suggest the multiverse might explain quantum mechanics strangeness, where particles exist in multiple states until observed. Could collapse of the quantum wave function simply be our awareness locking onto one branch of a vast branching reality? The multiverse forces us to confront the limits of science itself. Is it a cop-out, a way to dodge the question of why our universe seems so finely tuned? Or is it the next great paradigm shift, waiting for evidence we don't yet know how to gather? Until then, it remains the ultimate thought experiment, a mirror held up to our cosmic loneliness, reflecting the chilling possibility that everything we know is just one flicker in an endless sea of unseen worlds. Picture a beacon so bright it outshines an entire galaxy, a single point of light blazing with the fury of a trillion suns. This is a quasar, one of the most violent and luminous objects in the universe, capable of shining across billions of light years like a cosmic lighthouse. And here's the kicker: all that mind-bending energy erupts from a region no larger than our solar system. How is that even possible? The answer lies in the darkest, most ravenous monsters lurking at the hearts of galaxies, supermassive black holes. But not just any black holes, these are gluttons on a scale that defies imagination, devouring matter with such ferocity that they turn destruction into light. At the core of every quasar sits a supermassive black hole, weighing anywhere from millions to billions of times the mass of our Sun. These aren't the quiet voids we often imagine. They're ringed by swirling disks of superheated gas and dust, accretion disks where temperatures hit millions of degrees. As material spirals inward, friction and magnetic fields rip particles apart, creating a maelstrom of energy. But here's where the mystery deepens. Quasars don't just glow from their accretion disks. They fire jets of plasma at near light speed, shooting from their poles like cosmic blowtorches, stretching thousands of light years into space. These jets are so powerful they can carve through intergalactic gas, leaving scars visible across the cosmos. Yet the math still doesn't add up. Even with all that infalling matter, quasars shouldn't be this efficient at converting mass into energy. Einstein's famous equation, E equals mc squared, tells us matter can release energy when annihilated, but quasars seem to crank that process up to 11. One theory points to the black hole's spin. A rotating monster could twist space-time around it like a vortex, slingshotting material outward with terrifying force. Others suggest magnetic fields act as particle accelerators, channeling energy into those blistering jets. And then there's the wild card. What if some quasars are tapping into dark matter, or even energies we haven't discovered yet? Quasars aren't just ancient relics either. The brightest ones flared to life when the universe was young, a billion years after the Big Bang, which poses another puzzle. How did supermassive black holes grow so colossal so fast? Did they feast on dense primordial gas, or were they born big, collapsing directly from giant clouds in the early cosmos? Every new quasar we discover adds pieces to this puzzle, revealing how black holes and galaxies grew up together, shaping each other's destinies. What's clear is this: quasars are more than just cosmic oddities. They're windows into the most extreme physics in the universe, laboratories where gravity, magnetism, and sheer chaos collide. And until we unravel their secrets, they'll keep burning as reminders of how much we still don't understand about black holes, about energy, and about the violent beauty hidden in the heart of the dark. Every second, trillions of invisible bullets rip through Earth and through you at nearly the speed of light. These aren't sci-fi weapons, but cosmic rays, high-energy particles, mostly protons, flung across the universe with forces that dwarf anything our most powerful particle accelerators can produce. Some carry energy so absurd, they're comparable to a major league fastball compressed into a single subatomic particle. The mystery: we still don't know exactly what cosmic slingshot is firing them at us. For over a century, scientists have chased these ghostly projectiles back to their origins. The lowest energy rays likely come from our own sun, spat out during solar flares. Mid-range ones probably hitch rides on shockwaves from exploding stars' supernova, where chaotic magnetic fields act like particle accelerators, revving them up to terrifying speeds. But the real enigmas are the ultra-high-energy cosmic rays, packing millions of times more punch than anything CERN Large Hadron Collider can muster. These rare titans, hitting Earth about once per square kilometer per century, defy easy explanation. One leading suspect: active galactic nuclei, and the frenzied hearts of distant galaxies where supermassive black holes gulp down matter and belch out plasma jets. Picture a black hole's accretion disk spinning at relativistic speeds, twisting magnetic fields into cosmic rubber bands that snap, flinging particles across the universe. Another candidate, gamma ray, bursts the universe's most violent explosions, where collapsing stars or colliding neutron stars might unleash particle tsunamis. There's even speculation about exotic sources like decaying dark matter or defects in spacetime itself. Yet pinning them down is like tracing a bullet's path after it's ricocheted through a million halls of mirrors. Cosmic rays are charged, meaning interstellar magnetic fields bend their trajectories into indecipherable spirals by the time they reach us. So instead of looking at the particles directly, astronomers hunt for their air showers, cascades of secondary particles created when rays smash into Earth's atmosphere. Giant observatories like the Pierre Auger Array in Argentina spread thousands of detectors across miles of desert, waiting for these rare, telltale splashes. The stakes: cosmic rays aren't just celestial curiosities. They've meddled with Earth's history, potentially triggering mutations in DNA and influencing evolution. They're also a hazard for future Mars colonists, bathing unprotected travelers in radiation. And if we ever find their sources, we might unlock new physics, processes far more energetic than anything we can recreate on Earth. Until then, they remain the universe's most elusive snipers, firing without a trace, leaving us to piece together the wreckage of their invisible war. Imagine squeezing the entire mass of the Sun into a sphere the size of a city, a neutron star so dense, a teaspoon of it would weigh as much as Mount Everest. Now picture this cosmic wrecking ball suddenly collapsing further, rebounding with such force that it unleashes an explosion visible across the universe. This is the heart of a supernova, a stellar detonation so powerful it outshines entire galaxies, forges heavy elements in its wake, and scatters the building blocks of life across the cosmos. Yet for all their spectacle, these cosmic bombs still guard stubborn secrets about how they ignite and erupt with such precision. Let's start with the two main characters in this drama, Type Ia and Core Collapse Supernova. Type Ia explosions are the universe's standardized bombs. They begin with a white dwarf, the burned-out corpse of a sun-like star, locked in a gravitational tango with a companion star. As the dwarf steals matter, it creeps toward a critical mass limit, about 1.4 times the sun's mass, known as the Chandrasekhar limit. Cross that threshold, and the dwarf can no longer support its own weight. But here's where things get messy. We used to think the explosion triggered cleanly, like a fuse burning inward until the entire star detonates in a runaway nuclear chain reaction. Recent simulations, though, suggest it's far sloppier. The dwarf might ignite asymmetrically, with flames erupting like popcorn kernels popping at random before merging into a firestorm. Worse, some observations show Type Ias ejecting material at speeds that don't match the tidy models, hinting at physics we're still missing. Then there's the core collapse variety, the last violent breaths of massive stars at least 8 times heavier than our Sun. These giants fuse elements layer by layer like an onion until their cores turn to iron, and iron is the universe's ultimate party pooper. It absorbs energy instead of releasing it during fusion. With the core's energy source snuffed out, gravity wins catastrophically. In milliseconds, the core implodes at nearly a quarter the speed of light, cramming a sun's worth of material into a sphere just 12 miles wide. But the core doesn't just sit there, it rebounds, sending a shock wave roaring outward. Theoretically, this shock should stall, crushed by infalling material. Yet somehow it doesn't. Somehow it resurrects itself, blasting the star's outer layers into space. How neutrinos, those ghostly particles that barely interact with matter, might play savior, dumping enough energy into the shock to revive it. Or maybe turbulent convection behind the shock acts like a cosmic bellows, reigniting the explosion. The devil's in the details. Why do some collapsing stars leave behind neutron stars while others birth black holes? Why do certain supernovae, like the bizarre Type I, wreathe themselves in thick shrouds of pre-explosion gas, glowing for years like cosmic road flares? And then there's the wild card, pair instability supernova, where stars so massive over 100 solar masses become their own antimatter factories, annihilating from the inside out in explosions so bright they make the Milky Way look like a candle. Every supernova we observe is a Rosetta Stone for decoding stellar life cycles, element creation, and even the expansion of the universe itself. Yet the more we learn, the clearer it becomes. These explosions are far stranger, far more varied than our textbooks ever suggested. They're not just deaths, they're celestial metamorphoses, scattering the ingredients for planets, life, and even future stars across the void. And until we crack their ignition codes, we're left watching the cosmos's most dazzling fireworks with only half the instruction manual. At the heart of our galaxy, hidden behind thick curtains of dust and gas, lurks a monster, a supermassive black hole named Sagittarius, a star, weighing in at a staggering 4 million times the mass of our Sun. For decades, astronomers could only infer its presence by watching stars whip around an invisible point at speeds that defy logic, some clocking in at over 15,000 miles per second, tracing orbits so tight they'd fit inside our solar system. Then, in 2019, the Event Horizon Telescope team did the unthinkable. They captured the first ever image of its shadow, a glowing ring of light warped by gravity around the black hole's abyss. But the closer we look, the weirder it gets. Take G2, for example, a mysterious, fast-moving object that initially seemed to be a simple gas cloud drifting toward Sagittarius, a star. When it swung perilously close in 2014, astronomers held their breath, expecting it to be shredded by tidal forces and light up the galactic center in a fiery spectacle. Instead, G2 defied expectations. It stretched like taffy, then kept going, emerging mostly intact. This bizarre resilience suggests it's not just a cloud, but something far stranger. Perhaps a star cloaked in thick gas, or even a pair of merging stars, their combined gravity holding them together against the black hole's pull. Then there's the enigma of the G objects, a growing family of cosmic oddities orbiting Sagittarius, a star that behave like stars but puff up like gas clouds when they near the black hole. Some scientists speculate these could be failed stars, their cores hidden beneath swollen atmospheres, while others wonder if they're the remnants of stellar collisions, their outer layers stripped away by violent encounters. Whatever they are, they're rewriting our understanding of how matter behaves in the most extreme gravitational environments, but the real jaw-dropper. The eerie stillness of Sagittarius, a star itself. Despite its colossal size, our galactic center is oddly quiet compared to the raging quasars in other galaxies. Why isn't it devouring matter and blasting out energy? One theory suggests it's in a cosmic drought, starved of fuel because nearby stellar winds and magnetic fields keep gas just out of reach. Or perhaps it feeds in fits and starts, gorging itself during rare feasts before lapsing back into dormancy. Every observation peels back another layer of mystery. Infrared and radio telescopes have spotted massive, magnetized filament structures hundreds of light-years long, strung around the galactic center like cosmic harp strings. No one knows what's vibrating them. Meanwhile, X-ray telescopes catch flickers of energy like echoes of long-ago meals, hinting at violent flares that lit up the galaxy thousands of years ago. What's clear is this: the Milky Way's heart isn't just a black hole. It's a cosmic laboratory, a place where gravity twists the rules, where objects we can't yet explain dance on the edge of oblivion. And until we solve its riddles, we're just beginning to grasp the forces that shape not just our galaxy, but all galaxies. Here's an enduring paradox of our solar system. Stand on the surface of the Sun. If you could survive its 6,000 degrees Celsius furnace, and you'd actually be colder than the surrounding atmosphere. That's right, the Sun's outer atmosphere, called the corona, is a blazing inferno reaching over 1 million degrees, hundreds of times hotter than the star's visible surface beneath it. This cosmic oven defies everything we know about heat transfer, where temperatures should drop as you move away from a heat source, not spike violently. It's like walking away from a campfire and suddenly stepping into a blast furnace. For decades, scientists have wrestled with this mystery, proposing two leading theories to explain the corona's extreme heat. The first revolves around magnetic reconnection, a process where the Sun's tangled magnetic field lines snap and realign like rubber bands stretched too far. Picture the Sun's surface as a bubbling cauldron of plasma, where magnetic fields loop and twist. When these stressed fields suddenly reconfigure, they release colossal bursts of energy, equivalent to millions of hydrogen bombs in mere seconds. This explosive reshuffling pumps heat into the corona, supercharging particles to unimaginable speeds. Evidence: solar flares and coronal mass ejections, those spectacular eruptions we observe, are the visible fingerprints of this violent magnetic rearrangement. Yet magnetic reconnection might not act alone. Enter wave heating, the idea that the Sun's surface churns like a stormy ocean, generating waves that ripple upward through its atmosphere. Some waves, like Alfvén waves named after Nobel laureate Hans Alfvén, are essentially vibrations of the Sun's magnetic field, carrying energy like a whip cracking. As these waves travel into the thinner corona, their energy compresses, converting motion into blistering heat. Think of it as shaking a jump rope harder and harder until it glows from friction. Recent observations by NASA's Parker Solar Probe, which touched the Sun's corona, detected these waves in action, their intensity spiking as predicted. But here's the twist: neither theory fully explains the corona's relentless heat. Magnetic reconnection events are sporadic, while the corona stays consistently scorching. Wave heating, meanwhile, struggles to account for how energy dissipates so efficiently across such vast distances. Some researchers now suspect a hybrid model, where both mechanisms work in tandem, with waves distributing energy broadly and reconnection events delivering intense local spikes. Others propose nanoflares, countless tiny explosions too small for our telescopes to spot, constantly reheating the corona like popcorn kernels popping in a cosmic microwave. The stakes are higher than just solving a stellar puzzle. The corona's behavior drives space weather, with eruptions capable of frying satellites and knocking out power grids on Earth. Understanding its heating could unlock predictions of solar storms, or even teach us about atmospheres around distant stars. For now, the sun keeps its secret close, its crown of fire burning bright against the dark, daring us to look deeper. Imagine a neutron star, a city-sized remnant of a supernova so dense it crushes atoms into a sea of neutrons, but then crank its magnetic field up to 11 million times stronger than anything we can create in labs. That's a magnetar, one of the universe's most terrifying and enigmatic objects. These cosmic powerhouses generate magnetic fields so intense they'd liquefy you from half the moon's distance away, ripping electrons from your atoms before you even knew what hit you. What makes them so violently magnetic? It starts with their birth. When a massive star collapses into a neutron star, its already strong magnetic field gets compressed along with everything else. Squeezing a star's magnetic field into a space a billion times smaller is like taking a rubber band and stretching it until it's microscopically thin, except here, the rubber band is made of space-time itself, twisted into knots of unimaginable tension. But magnetars take it further. Their cores might host a quantum soup of hyperconducting fluids, where protons and neutrons swirl in ways that amplify the magnetic chaos, turning the entire star into a dynamo of pure ferocity. Then there are the flares. In 2004, a magnetar 50,000 light-years away unleashed a blast so powerful, it briefly outshone the full moon despite being halfway across the galaxy. For 1/10 of a second, it released more energy than our sun emits in 100,000 years. These starquakes happen when the magnetar's crust, under unimaginable strain from twisting magnetic fields, finally cracks like a brittle pane of glass. The resulting snap sends shockwaves through the star's exterior, launching tsunamis of charged particles and gamma rays, but the weirdness doesn't stop there. Some magnetars seem to slow down too fast, their rotations decaying in ways that suggest their magnetic fields are literally breaking them like spinning a top in molasses. Others flicker with bizarre periodic signals, hinting at structures beneath their surfaces we can't yet model. And in rare cases, they might even disguise themselves as fast radio bursts, those millisecond cosmic screams we still don't fully understand. The scariest part, we've only spotted about 30 of these monsters in our galaxy, but statistically, there could be dozens more lurking in the dark. One closer than we'd like could, in theory, fry Earth's ozone layer with a single bad-tempered outburst. Yet for all their destructive potential, magnetars are also cosmic gold mines, natural laboratories where matter, magnetism, and gravity collide under conditions we'll never replicate on Earth. Untangling their secrets might rewrite the textbooks on electromagnetism itself. Until then, they'll keep lurking in the void, twisting the fabric of reality into knots we're only beginning to glimpse. Picture a newborn star still swaddled in the swirling leftovers of its own birth, a vast pancake-shaped cloud of gas and dust called a protoplanetary disk. This is the nursery where planets are born, and for decades we thought we had the recipe figured out. Tiny dust grains stick together, growing into pebbles, then boulders, then mountain-sized planetesimals, until gravity takes over and sculpts them into full-fledged worlds. But as we peer deeper into these cosmic cradles, we're realizing planet formation is messier, more violent, and far stranger than we ever imagined. Take that first step, how microscopic dust grains clump together. In theory, static electricity or chemical bonds should make them stick like cosmic Velcro. Yet experiments show a problem. Once these grains reach millimeter sizes, they bounce off each other in microgravity instead of merging, like trying to build a sandcastle with marbles. One solution might be dust traps, regions where gas pressure creates eddies that concentrate particles, giving them more time to collide and fuse, another wild card. Water ice and organic goo acting as cosmic glue, helping grains stick where dry rock would fail. Then comes the planetesimal mystery. How do pebbles jump from fist-sized rubble to objects hundreds of miles across? Some models suggest fleeting gravitational instabilities, patches of the disk so dense they suddenly collapse under their own weight, skipping the slow growth phase entirely. Others propose that turbulent winds ferry pebbles toward pressure bumps, where they pile up like snowdrifts until their collective gravity snowballs into protoplanets. The truth might be both, with different pathways dominating in different parts of the disk. And then there's the puzzle of hot Jupiters, gas giants that orbit laughably close to their stars, closer than Mercury is to our Sun. These shouldn't exist under classic formation models. That close to a star, the disk's heat and radiation should blow away lightweight gases before a Jupiter could form. The leading fix: these planets might have started life farther out, then spiraled inward due to drag from the gas disk, or gravitational tugs from other planets flung them into scorchingly tight orbits. Some might have even been ejected entirely, becoming rogue worlds drifting between the stars. The more we learn, the clearer it becomes. Planet formation isn't some orderly assembly line, but a chaotic construction site where gravity, chemistry, and luck collide. Every new exoplanet we find, from diamond worlds to styrofoam-like giants, adds another twist to the story. And until we can peer into more of these dusty stellar nurseries with telescopes like the James Webb, the universe will keep surprising us with how creative it can be when building new worlds. Time feels like the most reliable constant in our lives, ticking forward, second by second, never slowing or speeding up. But peel back the curtain of reality, and time becomes one of the universe's greatest illusions. Einstein's relativity shattered the idea of a universal clock, revealing that time stretches and compresses like taffy depending on how fast you're moving or how close you are to a massive object. Near a black hole, time crawls to a near standstill for an outside observer, while for you it'd feel like business as usual. Yet quantum mechanics, the rulebook for the subatomic world, paints a starkly different picture. There, time isn't a dynamic player, it's just a static backdrop, a parameter that doesn't bend or warp. So which is it, a flexible fabric or a rigid stage? The conflict between these two visions isn't just academic, it's a battle for the soul of physics itself. Then there's the arrow of time. Why does it always point forward? The laws of physics, bizarrely, work just fine in reverse. A collision of two particles looks perfectly normal whether you play it forward or backward. But try unspilling a glass of milk and suddenly time's direction feels set in stone. The secret might lie in entropy, the universe's tendency toward disorder. Early on, the cosmos was in an improbably low entropy state, like a perfectly stacked deck of cards. As the universe expands, that order unravels, creating the gradient we perceive as the flow of time. But here's the twist: entropy doesn't explain time's direction, it just correlates with it. Why did the universe start so ordered? That's like asking why the first domino was tipped in the first place. Some physicists propose time isn't fundamental at all, it's emergent, a side effect of deeper, timeless processes. Imagine watching a movie. The story unfolds because frames change, but the frames themselves are static. Could time be like that, an illusion created by quantum events updating reality in sequence? In loop quantum gravity, for example, space-time is pixelated, and time might arise from how these quantum pixels interact. Others, like proponents of string theory, suggest time could be holographic, encoded on the boundary of the universe like a cosmic DVD, the most radical idea. Time might not even exist at the fundamental level. The Wheeler-DeWitt equation, a tentative theory of quantum gravity, famously lacks a time variable altogether. In this view, what we call time could be a kind of collective hallucination, a way for conscious beings like us to make sense of a timeless, interrelated web of events. It's enough to make your head spin faster than a neutron star, until we reconcile relativity's malleable time with quantum mechanics' stubborn clock, or discover a deeper theory that unites them. Time remains a paradox. It's the river we're all floating on, yet no one can say for certain whether the river is real or just the current we invented to feel less adrift in the cosmos. The moon has always shown us the same face, its smooth, dark plains gazing down like a silent guardian. But flip it around and the far side tells a completely different story. A battered, cratered wasteland, rough and jagged where the near side is polished. This split personality is one of the solar system's most striking puzzles. Why would two sides of the same world look so alien to each other? The answer may lie in a cosmic accident billions of years ago, when the moon was still young and the solar system was a shooting gallery of rogue asteroids. First, let's talk tidal locking, the reason we only see one face of the moon at all. Over millions of years, Earth's gravity tugged unevenly on the moon's lumpy mass, slowing its rotation until it matched its orbit. Now it spins exactly once per trip around Earth, like a dancer keeping perfect eye contact. But this gravitational embrace didn't just freeze the moon's rotation, it shaped its geography. Early in its history, the moon's near side, constantly facing Earth, was kept warmer by our planet's reflected heat and radiation. That warmth might have kept the crust slightly softer, allowing ancient lava flows to fill in impact scars and create the smooth Maria we see today. The far side, meanwhile, hardened faster, its crust growing thicker and more rigid, leaving it exposed to the relentless pummeling of space debris. Then there's the giant impact theory. Some scientists argue the far side's ruggedness stems from a catastrophic collision with a second moon, a smaller companion that once shared our sky. When the two crashed in slow motion, the impact wouldn't have left a crater. Instead, the smaller moon might have splattered like wet clay across the far side, piling up an extra layer of mountainous rubble. Evidence: the far side's crust is up to 50 miles thicker than the near side's, and missions like China's Chang 4 have found minerals there that don't match the familiar volcanic basalts of the near side. But the story gets stranger. Recent gravity maps reveal massive, dense blobs lurking beneath the far side's surface, buried remnants of an ancient inferno. One leading idea suggests these could be the carcasses of colossal impactors that struck the moon so hard. Their metal-rich cores sank into the mantle and solidified, leaving behind ghostly gravitational signatures. Or perhaps they're leftovers from the moon's own violent birth, when a Mars-sized object, Theia, smashed into Earth and flung molten debris into orbit. Whatever the cause, the moon's two-faced nature is a reminder that even our closest cosmic neighbor hides secrets written in scars and shadows. And until future missions dig deeper, literally, we're left piecing together a geological detective story where every clue just leads to more questions. Most planets have the luxury of orbiting a star, basking in its warmth like children around a campfire. But not rogue planets. These cosmic nomads wander the galaxy alone, untethered to any sun, drifting through the eternal night like ghosts. Some were born this way, collapsing directly from gas clouds too small to ignite into stars. Others were violently evicted from their home solar systems, flung into the void by gravitational encounters with sibling planets or passing stars. No sunlight reaches them, no seasons mark their years, yet despite their frozen exile, these orphaned worlds might be anything but dead. Picture a rogue planet, dark and distant. Its surface is a frozen wasteland where temperatures hover just a few degrees above absolute zero, cold enough to freeze nitrogen solid, but dive beneath the ice and things get interesting. Many of these worlds, especially those with masses comparable to Earth or Neptune, could retain enough internal heat from radioactive decay or tidal flexing to maintain vast subsurface oceans. Just look at Europa and Enceladus in our own solar system. icy moons warmed by their gas giant's gravity. A rogue planet wouldn't have a Jupiter to squeeze it, but the sheer insulation of a miles-thick ice crust might trap geothermal heat for billions of years. That raises a tantalizing possibility. Could life exist in these lightless abysses? On Earth, entire ecosystems thrive around hydrothermal vents far beyond the reach of sunlight. If rogue planets harbor similar environments, with liquid water, chemical energy sources, and stable conditions, they might be the ultimate survivors. Some could even outlast stars themselves, drifting through the galaxy long after their stellar siblings have burned out. The real challenge is finding these invisible drifters. Without a star to illuminate them, rogue planets are nearly impossible to spot with traditional telescopes. But astronomers have tricks. One method relies on microlensing, watching for the subtle warping of starlight as a rogue planet's gravity bends it like a lens. Already, surveys like OGLE and Japan's MOA project have bagged a few candidates, including one roughly the mass of Earth. NASA's upcoming Nancy Grace Roman Space Telescope could discover hundreds more, painting a clearer picture of how many starless worlds lurk in the dark. What's wild is the math. Some estimates suggest rogue planets might outnumber stars in the Milky Way by a factor of 20. That's trillions of untethered worlds, a hidden archipelago in the cosmic ocean. Whether they're sterile ice balls or teeming with extremophiles, one thing's certain: the galaxy is far stranger and far more crowded than we ever imagined. Look up at the night sky, really look and try to grasp what you're seeing. Every star, every galaxy stretches back farther than light itself has traveled since the dawn of time. Now ask yourself, does it ever end? Is space infinite, or is there some cosmic edge, some boundary beyond which there's nothing? Scientists have wrestled with this question for centuries, and today we're closer than ever to an answer, or at least to understanding how slippery the question really is. Let's start with the data. The universe's shape isn't just a philosophical curiosity, it's something we can measure. Imagine drawing a triangle on a cosmic scale. On Earth, its angles add up to 180 degrees, but in curved space that sum changes, more for positive curvature like a sphere, less for negative curvature like a saddle. When cosmologists perform this experiment using the cosmic microwave background, the afterglow of the Big Bang, they find a universe so flat, the angles add up to 180 degrees within a razor-thin margin of error. Flat geometry suggests one of two mind-bending possibilities. Either the universe is infinite, stretching forever without boundary, or it's finite but unbounded, like the surface of a balloon so vast, its curvature is undetectable to us. But here's where things get thorny. If the universe is finite, what's outside it? The question might be meaningless. Just as a fish can't conceive of outside its ocean, our brains struggle to imagine boundaries to space-time itself. Some theories propose higher dimensions, a multiverse where our universe is one bubble among countless others. Others suggest the cosmos loops back on itself, so traveling far enough in one direction would bring you full circle, like an ant walking around a globe. Then there's the observable universe, the portion we can see, limited by light's finite speed. Beyond about 93 billion light-years in diameter, space expands so fast that light from those regions will never reach us. But this horizon isn't a physical edge, it's just the limit of our vision. The total universe could be vastly larger, even infinite, and if it is, that opens dizzying doors. An infinite cosmos would mean infinite repeats. Somewhere, every possible arrangement of particles would exist, including identical copies of you reading identical copies of this script. But infinity isn't just a math problem, it's a mirror reflecting our deepest biases. We evolved in a finite world where everything has edges and ends. The universe owes us no such familiarity. Whether it's boundless or bounded, one thing's certain: reality refuses to fit neatly into the boxes our minds insist on building. And until we crack the code of dark energy, quantum gravity, or whatever lies beyond, we're left staring into the abyss, wondering if it stares back or stretches forever. Back in the 1970s, as the Pioneer 10 and 11 spacecraft hurtled toward the outer solar system, scientists noticed something bizarre. Their trajectories were ever so slightly off. Minute by minute, mile by mile, both probes were slowing down more than Newton's laws predicted, as if an invisible hand were tugging them backward. This tiny discrepancy, barely a fraction of a millimeter per second squared, became known as the Pioneer Anomaly, a cosmic puzzle that baffled physicists for decades. At first, the culprit seemed obvious: heat. The probe's plutonium-powered generators emitted warmth, and even the faintest thermal radiation could act like a mini thruster pushing against the spacecraft. But when engineers crunched the numbers, the math didn't quite add up. The heat's effect was real, but it only accounted for part of the deceleration. So where was the rest coming from? Some theorists proposed wilder explanations: leaks from fuel tanks, undiscovered quirks of relativity, even the gravitational pull of hidden dark matter clumps. Others whispered about more exotic possibilities, like flaws in our understanding of gravity itself. Then came the eureka moment. In 2012, a team meticulously reconstructed the probe's thermal profiles, factoring in every watt of radiation bouncing off their asymmetrical surfaces. The verdict: the anomaly wasn't mysterious at all, just fiendishly complex. Uneven heat flow, radiating more from one side of the spacecraft than the other, had acted like an invisible brake. Case closed, not entirely. While thermal radiation solved most of the puzzle, a whisper of uncertainty lingers. Future missions like NASA's upcoming interstellar probes will need even finer precision to avoid similar surprises. The Pioneer Anomaly's legacy isn't just about solved equations, it's a lesson in humility. Even in spaceflight, where we calculate trajectories to the nanometer, the universe finds ways to remind us there's always another layer to peel back, another shadow of mystery waiting just beyond the data. And sometimes the smallest deviations hold the biggest revelations. Water is the elixir of life. It covers 70% of Earth's surface, fills our cells, and shapes our climate. But here's the twist: our planet shouldn't have this much water. Born in the scorching inner solar system, where temperatures were too high for water ice to survive, Earth was a dry, molten rock in its infancy. So how did our oceans get here? The answer lies in a cosmic delivery service with two prime suspects, comets and asteroids, and the debate over which one brought our water is far from settled. First, the case for comets. These cosmic snowballs, hailing from the frozen outskirts of the solar system, are packed with water ice. When young Earth was still cooling, a barrage of comets, leftovers from the solar system's formation, could have crashed into our planet, melting on impact and filling ancient basins. The Rosetta mission, which orbited Comet 67P, seemed to support this idea until it didn't. The water vapor spewing from the comet's surface had a different chemical fingerprint than Earth's oceans. Specifically, it contained too much deuterium, a heavy isotope of hydrogen. While some comets might match Earth's water ratio, the majority don't, leaving a gap in the theory. Then there are asteroids, rocky, carbon-rich bodies from the asteroid belt. Unlike comets, these objects contain water locked inside minerals, not as free ice. When they collide with Earth, their hydrated minerals break down, releasing water vapor that eventually condenses into oceans. Samples from certain meteorites, like the Murchison chondrite, reveal water with a deuterium ratio eerily similar to Earth. And here's the clincher. Models suggest the inner solar system was bombarded by asteroids during the late heavy bombardment, some 4 billion years ago. A chaotic era that could have delivered enough water to fill our seas. But the puzzle isn't so simple. If asteroids were the main carriers, why is Earth's water so abundant compared to our neighbor Mars, which presumably got hit by the same space rocks? Some scientists propose a hybrid scenario. Maybe water arrived from both sources, with asteroids dominating early deliveries and comets topping things off later. Others point to an even wilder idea, that Earth retained trace amounts of water from its own formation, trapped deep in the mantle and released over eons through volcanic outgassing. The stakes go beyond our own planet. If we unravel Earth's water story, it could reveal which exoplanets are truly habitable. After all, a world's water source shapes its chemistry, climate, and even the potential for life. For now, the mystery lingers, a reminder that the most familiar things can hold the deepest cosmic secrets. Black holes suck everything in, but what if the universe had cosmic fountains, spewing out matter and energy instead of devouring them? That's the tantalizing idea behind white holes, the hypothetical twins of black holes flipped inside out. Where a black hole's event horizon marks a point of no return, a white hole's boundary would be a place of no entry. Nothing could cross inside, only erupt outward in a torrent of radiation and particles. These bizarre objects aren't just science fiction. They emerge as mathematical solutions to Einstein's equations of general relativity, the same framework that predicted black holes over a century before we photographed one. Yet, unlike their dark siblings, white holes remain purely theoretical, glimpsed only in the abstract landscapes of physicists' notebooks. One way to imagine a white hole is as a black hole running in reverse, like hitting rewind on a video of matter vanishing beyond an event horizon. If you could play the tape backward, you'd see energy and particles bursting back into existence, ejected from a singularity instead of collapsing into one. Some theories suggest white holes could be the other end of a black hole, connected by an Einstein-Rosen bridge, the fancier term for a wormhole. Picture a tunnel where matter falls into a black hole in one corner of space-time, only to be vomited out of a white hole somewhere else, perhaps in another universe or another time entirely. It's the ultimate cosmic shortcut, or at least it would be, if any of it were real. Here's the catch: white holes violate the second law of thermodynamics, which says entropy, a measure of disorder, always increases over time. A white hole would essentially reverse entropy, spewing out perfectly ordered energy from nowhere, like a shattered glass reassembling itself midair. Nature tends to frown on such tidy miracles. That's led some physicists to argue white holes can't exist, or if they did, they'd instantly collapse into black holes under the weight of their own impossibility. Yet the idea refuses to die. Some researchers speculate that the Big Bang itself could have been a white hole event, a singularity erupting into the universe we know. Others suggest that quantum gravity effects, which kick in at the tiniest scales, might stabilize white holes long enough to leave traces in the cosmos. A few even propose that fast radio bursts, those millisecond blasts of energy from deep space, could be white holes burping up remnants of long-vanished matter. The truth is, we have zero observational evidence for white holes. No telescope has ever caught one in the act of cosmic expulsion, but that's part of their allure. They're a reminder that the universe's rulebook might still have pages we haven't read. Until we crack quantum gravity or stumble upon a white hole's radiant signature, they'll linger at the edge of reality, dazzling, improbable, and utterly defiant of everything we think we know. Venus is a world of contradictions, a planet that spins slower than any other in our solar system, yet its upper atmosphere races around at hurricane speeds more than 60 times faster than the planet itself rotates. Imagine Earth's jet streams, but dialed up to a nightmare setting, with winds screaming across Venus cloud tops at over 200 miles per hour, completing a full lap of the planet every 4 Earth days, while the surface below takes a sluggish 243 days to turn just once. This phenomenon, called superrotation, defies everything we know about atmospheric mechanics. On Earth, our weather systems are largely driven by the planet's rotation, but Venus winds operate on their own chaotic schedule, like a record spinning at the wrong speed while the turntable barely moves. The puzzle begins with Venus' thick, suffocating atmosphere, a crushing blanket of carbon dioxide 90 times denser than Earth's, shrouded in clouds of sulfuric acid. All that mass should, in theory, be tightly coupled to the planet's rotation, dragged along by friction and surface topography. Yet something is injecting enormous energy into the upper atmosphere, overpowering this expected lockstep. One leading suspect is thermal tides, pressure waves generated by the sun's relentless heating on the planet's day side, which ripple through the atmosphere like a cosmic slap. As sunlight bakes the thick Venusian air, temperature differences between day and night sides could drive these colossal wind patterns, accelerated further by the planet's lack of surface features to slow them down. No mountains, no oceans, just smooth plains offering no resistance to the atmospheric juggernaut. But here's where it gets stranger. Models that account for solar heating still can't reproduce the full ferocity of Venus winds. Some hidden engine seems to be revving the system beyond predicted limits. Could the answer lie in the planet's bizarre cloud chemistry? Venus sulfuric acid clouds absorb ultraviolet light, creating layers of intense heat gradients that might act like invisible pistons, pumping momentum into the upper winds. Or perhaps there's a feedback loop involving mysterious gravity waves, not to be confused with gravitational waves where disturbances in the lower atmosphere surge upward, dumping energy like fuel into a turbocharger. Then there's the wild card. Venus' slow rotation might actually be feeding the chaos. With so little rotational force to organize weather patterns, the atmosphere could be free to run amok, untamed by the stabilizing influence of Coriolis effects that shape Earth's jet streams. Probe missions like Japan's Akatsuki orbiter have spotted massive, bow-shaped structures in the clouds stretching for thousands of miles, atmospheric monsters that could be key to transferring energy between layers. Yet even with these clues, the full picture remains as hazy as Venus' own skies. What makes this mystery more than just planetary trivia? Understanding superrotation could reshape how we study exoplanets. Many of the world's orbiting distant stars are likely Venus-like, locked in thick, toxic shrouds with atmospheres behaving in ways we've barely begun to map. If we crack Venus' secrets, we might unlock a universal language for decoding alien weather systems. Until then, the planet keeps spinning its enigma, a swirling riddle wrapped in acid clouds, daring us to look deeper. Among the countless particles zipping through space, a few stand out like cosmic anomalies, ultra-high energy cosmic rays, packing enough punch to rival a major league fastball in a single subatomic particle. These tiny bullets, mostly protons, scream across the universe with energies exceeding 100 million trillion electron volts, a number so absurd it defies the limits of what our most powerful particle accelerators can produce. To put that in perspective, a single one of these particles carries the kinetic energy of a brick dropped from waist height, compressed into a speck smaller than an atom. And the real mystery, we still don't know what celestial cannon is firing them at us. The hunt for these extreme particles reads like a detective story with missing clues. Normally, cosmic rays from our own sun or nearby supernova are easy to trace. Their lower energies make them bounce along predictable paths like pinballs in a magnetic field. But ultra-high-energy cosmic rays are different. Their staggering momentum lets them punch straight through galactic magnetic fields without veering off course, which should make their origins obvious. Yet when astronomers trace their trajectories backward, they often point to empty space. No known cosmic powerhouse sits at the end of those paths, leaving scientists scratching their heads. The prime suspects are active galactic nuclei, the violent hearts of distant galaxies where supermassive black holes gulp down matter and spew out jets of plasma moving at nearly light speed. These jets could act as natural particle accelerators, revving up protons to insane energies through twisting magnetic fields. Imagine a cosmic slingshot where magnetic turbulence acts like rubber bands stretched to their breaking point, snapping particles forward with unfathomable force. Another contender, gamma ray, bursts the universe's most cataclysmic explosions where colliding neutron stars or collapsing hypergiants might unleash particle shockwaves powerful enough to rival black hole jets. Yet even these extreme engines struggle to explain the highest energy rays. Some particles hit with such force, they challenge something called the Greisen-Zatzepin-Kuzmin-Gzk limit, a theoretical ceiling based on how cosmic rays should lose energy over vast distances by smashing into the cosmic microwave background, the leftover glow of the Big Bang. Particles beyond this limit shouldn't reach Earth unless they come from nearby, but some do, and their paths lead nowhere obvious. Could their sources be hidden behind dust clouds? Or are we dealing with entirely new physics, exotic phenomena like decaying dark matter, cosmic strings, or defects in spacetime itself? The race to catch these particles in action is a feat of ingenuity. Since they're too rare to detect directly, scientists build sprawling observatories like the Pierre Auger Array in Argentina, an army of detectors spread across 3,000 square kilometers, waiting for the telltale cascade of secondary particles created when an ultra-high-energy cosmic ray slams into Earth's atmosphere. These air showers rain down billions of particles, allowing researchers to reconstruct the original ray's energy and direction. Even then, luck plays a huge role. These events hit each square kilometer of Earth only about once per century. What's at stake goes beyond curiosity. If we pin down their origins, we might unlock new chapters in astrophysics processes far more energetic than anything we can replicate in labs. These particles could also be messengers from the universe's most hidden corners, carrying clues about black hole dynamics, dark matter, or even the birth cries of primordial universes. For now, they remain nature's most elusive snipers, firing without warning from the dark, daring us to decode their origins. Imagine a cosmic shortcut, a tunnel punched through the fabric of space itself, connecting two distant points in the universe like a folded piece of paper with a hole poked through it. This is the tantalizing promise of wormholes, a concept that's bounced between science fiction and serious physics for over a century. While Einstein's equations allow for these space-time bridges mathematically, the real question is, could they actually exist? And if they do, how would we ever spot one? The first hurdle is stability. Traditional wormholes, those predicted by general relativity, would collapse instantly under their own gravitational weight unless propped open by something with negative energy, a property that defies everyday intuition. Picture trying to hold open a tunnel with repulsive gravity, like using anti-gravity concrete to shore up the walls. Exotic matter, a theoretical substance with negative mass, could do the trick, but we've never observed it in nature. Some quantum theories suggest fluctuations in vacuum energy might briefly create microscopic wormholes, but scaling them up to human traversable sizes would require energies beyond anything we can imagine. Yet suppose wormholes do persist, how would they betray their presence? One telltale sign could be gravitational, lensing the bending of light around massive objects, but with a bizarre twist. A wormhole's unique geometry might create a double lensing effect. Unlike a black hole, which distorts light from objects behind it into a single ring, an Einstein ring, a wormhole could produce multiple rings or even mirror images of the same background galaxy, as light wraps around both mouths of the tunnel. The James Webb Space Telescope's keen eye might spot these anomalies in deep field images, especially if a wormhole's entrance is framed against a dense star field. Then there's the spectral fingerprint. Wormholes threaded with exotic matter could warp spacetime so severely that they'd emit a distinct pattern of Hawking radiation, different from black holes' emissions. Telescopes hunting for gamma-ray signatures or anomalous heat maps in seemingly empty patches of space might catch whispers of these phantom tunnels. Even stranger, if a wormhole's far end is moving relative to us, say, orbiting another star, its entrance could flicker or Doppler shift light in ways no natural object should. But the ultimate smoking gun, motion without cause. If a star or gas cloud seems to dance under the influence of an invisible partner, but conventional calculations can't account for its movement, it might be tethered to a hidden wormhole's gravitational pull. Recent studies even suggest that wormholes could vibrate like drum heads when disturbed, emitting gravitational waves detectable by observatories like LIGO, though these signals would be subtler than the black hole collisions we've spotted so far. The truth is, wormholes sit at the edge of known physics, a playground where relativity and quantum mechanics collide. They're mathematically seductive yet observationally elusive, cosmic maybes that refuse to be dismissed entirely. Until we find one, or rule them out definitively, they'll remain the universe's most glamorous hypothetical, shortcuts through space teasing us with the possibility that the longest journeys might have secret backdoors. Imagine the universe as a loaf of raisin bread baking in an oven. At first, the raisins are close together, but as the dough expands, they move apart. Now picture that oven has a hidden turbo button, one that makes the bread rise faster and faster over time, defying all expectations. That's exactly what astronomers discovered in the late 1990s when they measured distant supernova and realized the universe isn't just expanding, it's accelerating its expansion, as if some invisible force is pressing harder on the cosmic gas pedal with each passing moment. Dark energy is the placeholder name we've given to this mysterious driver, but its true identity remains one of cosmology's greatest enigmas, the leading theory. Vacuum energy, a concept rooted in quantum mechanics that suggests empty space isn't truly empty. At the smallest scales, particles flicker in and out of existence, creating a seething foam of energy that permeates the cosmos. According to Einstein's equations, this energy could produce a repulsive force pushing space apart. But there's a glaring problem. When physicists calculate how strong this effect should be, the numbers overshoot observations by a factor of 10 to the power of 120. That's the worst theoretical prediction in the history of science, akin to expecting a gentle breeze and getting a hurricane powerful enough to shred galaxies. Clearly, we're missing something fundamental. Enter quintessence, a more flexible contender named after the elusive fifth element of ancient philosophy. Unlike vacuum energy, which remains constant over time, quintessence proposes a dynamic field that evolves, its strength waxing or waning as the universe ages. Picture it as a cosmic thermostat, subtly adjusting its push against gravity's pull. Some models even suggest quintessence could one day switch signs, flipping from repulsive to attractive and potentially reversing the universe's expansion into a catastrophic big crunch. Yet despite its elegance, quintessence struggles to explain why acceleration began precisely when it did around 5 billion years ago, after eons of slower expansion. The stakes couldn't be higher. Dark energy accounts for 68% of the universe's total energy budget, yet we still don't know whether it's a property of space itself or something entirely foreign to our current physics. Future missions like the European Space Agency's Euclid telescope aim to map dark energy's influence with unprecedented precision, hunting for clues in the large-scale structure of galaxies. Will we find that vacuum energy's paradox points to undiscovered dimensions or a flaw in quantum field theory? Or will quintessence's subtle variations reveal a cosmos far more dynamic than we ever imagined? The answer won't just rewrite textbooks, it will redefine our place in a universe whose ultimate fate hangs in the balance. Neutron stars already push the limits of cosmic weirdness, crushing a sun's worth of mass into a sphere the size of Manhattan, where atoms collapse into a sea of pure neutrons. But what if nature found a way to squeeze matter even further? Enter strange stars, hypothetical celestial monsters that could make neutron stars look tame. These theoretical objects, also called quark stars, might consist of something even more exotic. Strange matter, a primordial soup where the very building blocks of protons and neutrons break apart under unimaginable pressure, melting into free-floating quarks swimming in a quantum ocean. Quarks normally come in teams 3 bound tightly together by gluons to form protons and neutrons. The intense gravity inside neutron stars is thought to overwhelm these bonds, creating a superfluid of neutrons packed like sardines. But strange matter takes this a step further. At densities beyond even neutron stars, some theories suggest quarks could shed their team loyalties entirely, mingling freely across a bizarre new state where up, down, and strange quarks, one of the 6 known quark flavors, mix indiscriminately. This strange matter would be staggeringly dense, possibly the most stable form of matter in the universe. A single sugar cube's worth could outweigh Mount Everest. The implications would shatter astrophysics. Strange stars, if they exist, might masquerade as neutron stars but with telltale differences. Their surfaces could be smoother, lacking the mountains and fissures caused by neutron-rich crusts. Their cooling rates might defy neutron star models, since quark interactions radiate heat differently. Most intriguingly, they could sport ultra-thin crusts of normal matter floating like oil on water, occasionally cracking open in starquakes that release bursts of energy we might detect as gamma-ray flares or gravitational waves. The problem, we've never confirmed one. Candidates like XTJ 1739-285 and 3C58 tantalize researchers with their odd properties, but proof remains elusive. Strange matter's stability poses another riddle. If it's truly the universe's preferred state, could it be contagious? Hypothetically, a strange star's debris colliding with normal matter might infect it, converting entire planets or stars into strange matter in a runaway chain reaction. Fortunately, Earth hasn't been hit by such shrapnel, or we wouldn't be here to ponder it until we catch a smoking gun, perhaps gravitational waves from a strange star merger, or a telescope spotting a star too small to be a neutron star yet too dense to be anything else. These cosmic enigmas will hover at the edge of discovery. They remind us that for all we know about the universe, the most extreme chapters of its physics might still be waiting in the dark, daring us to look deeper. Deep in the archives of cosmic history, there's a growing mystery that's keeping astronomers awake at night. Galaxies that shouldn't exist. Thanks to the James Webb Space Telescope's revolutionary infrared vision, we're seeing fully formed galaxies dating back to when the universe was barely 3% of its current age. These cosmic cities, brimming with stars, appear to have assembled themselves impossibly fast, some in just 200 million years after the Big Bang. That's like finding a skyscraper in the middle of the Stone Age, built with tools that shouldn't have existed yet. The traditional story of galaxy formation, called the hierarchical model, paints a gradual picture. Tiny clumps of dark matter slowly merge over billions of years, pooling gas to form stars, which then build galaxies through countless collisions. It's a cosmic game of bumper cars where bigger structures emerge from smaller ones. But JWST discoveries smash this tidy timeline. Galaxies like Glass Z13, spotted when the universe was only 300 million years old, already contain billions of stars packed into mature spiral and elliptical shapes. They're not the fragile prototypes we expected, they're finished products gleaming in the cosmic dawn. So where did our models go wrong? One radical idea suggests dark matter isn't what we think. Perhaps it interacts with itself through unknown forces, clumping together faster than predicted. Alternative theories propose heavy, dark matter particles that would collapse into dense seeds earlier, giving galaxies a head start. Others look to the universe's infancy. Maybe the first stars were monstrously huge, burning bright and dying young in supernova that flooded space with metals, jump-starting later generations of star formation at breakneck speed. Then there's the wild card, cosmic filaments. The early universe wasn't a uniform soup. It had wrinkles, dense threads in the cosmic web where gas could flow like rivers into waiting gravitational wells. If these filaments were thicker or more efficient at channeling material than we've assumed, galaxies might have gorged themselves on ready-made stellar fuel, skipping the usual growing pains. Some simulations now show that under just the right conditions, giant galaxies could indeed form shockingly fast, like time-lapse footage of a flower blooming in seconds. The stakes are astronomical. If these precocious galaxies force us to rewrite the rules of cosmic evolution, it could reshape everything from how black holes grow to when life's building blocks first appeared. Future JWST observations will hunt for even earlier galaxies, probing the shadows of the cosmic dark ages. Each discovery peels back another layer of the mystery, revealing a universe far more inventive and far less predictable than we ever imagined. All the ingredients for life seem to be scattered across the cosmos like seeds in fertile soil. Water molecules drift through interstellar clouds. Complex organic compounds coat the surfaces of asteroids. Planets orbit within habitable zones around nearly every star we've studied. With odds like these, the universe should be teeming with civilizations. So why does the silence feel so deafening? This is the Fermi Paradox at its most haunting, and with every new discovery, it only grows more perplexing. Recent exoplanet surveys have turned up thousands of worlds that could cradle life. Take Kepler 442b, a rocky planet basking in the gentle glow of its orange dwarf star, sitting snugly in the liquid water zone. Or TRAPPIST-1e, one of 7 Earth-sized planets orbiting a cool red star, where tidal forces might keep oceans churning beneath icy shells. Statistically, there could be billions of potentially habitable worlds in our galaxy alone. Yet after 6 decades of SETI radio telescopes scanning the skies, the airwaves remain eerily quiet. No signals, no megastructures, not even a whisper of cosmic small talk. The search has grown more sophisticated. Instead of just listening for radio waves, astronomers now hunt for technosignatures, clues of advanced civilizations etched into the fabric of space itself. They scan for Dyson spheres, hypothetical energy harvesting structures that might dim a star's light in telltale ways. They analyze atmospheric chemistry of distant exoplanets, looking for industrial pollutants like CFCs that nature couldn't produce. Some even search for alien city lights flickering on the dark sides of tidally locked worlds. So far, nothing, but here's what keeps scientists up at night. Maybe we're not looking for the right things. An advanced civilization might communicate with neutrino beams or quantum entanglement, technologies as foreign to us as radio would have been to dinosaurs. Or perhaps they've transcended physical forms, uploading their consciousness into digital realms we can't perceive. There's a darker possibility, too, that intelligent life inevitably self-destructs, whether through war, environmental collapse, or unchecked artificial intelligence. The Great Filter theory looms large. It suggests some nearly insurmountable barrier prevents life from progressing to interstellar communication, whether it's the rarity of abiogenesis, the fragility of complex ecosystems, or the lethality of technological adolescence. The chilling question, is the filter behind us making us cosmic lottery winners or ahead of us, waiting to snuff out our potential? For all our searching, the universe offers no easy answers. The more we learn, the more the question splits into fractals of possibility. Are we alone because life is vanishingly rare, because intelligence is fleeting? Or because the cosmos is vaster and stranger than we've dared to imagine? The silence isn't just a mystery, it's a mirror, forcing us to confront how little we understand about our place in the dark. And until we find proof otherwise, the stars will keep their secrets, leaving us to wonder if we're the universe's only children, or simply its youngest. From the eerie silence of the cosmos to the violent tantrums of magnetars, from the phantom tug of dark matter to the cosmic mirage of wormholes, we've journeyed through 30 of the universe's most profound mysteries, each one a frontier where human curiosity crashes headlong into the limits of our understanding. These aren't just gaps in a textbook, they're pulsating enigmas that redefine reality itself. Think about it, black holes shouldn't vanish, yet Hawking radiation says they do. The universe shouldn't be accelerating, yet dark energy laughs at our equations. Life should be everywhere, yet the cosmos remains stubbornly, achingly quiet. Every question we've explored, whether it's the origins of Earth's water or the fate of rogue planets, is a testament to how much we don't know, and that's what makes science so thrilling. These mysteries aren't dead ends, they're invitations. Each one is a crack in the facade of the known universe, letting in just enough light to tempt us closer. Maybe you're captivated by the haunting elegance of white holes, or maybe the frenzied winds of Venus keep you up at night. Perhaps you're drawn to the existential dance of matter and antimatter, or the spine-tingling possibility that we're living in a multiverse. Whatever sparks your wonder, remember, every great discovery in history began as a question someone refused to stop asking. So stay curious. The universe isn't done surprising us, not even close. New telescopes, probes, and AI-driven breakthroughs are peeling back layers of reality we didn't even know existed. Want to be part of the next big revelation? Hit subscribe so you don't miss a single update as we chase these cosmic riddles down the rabbit hole, and drop a comment below which mystery left you awestruck. The phantom pull of the pioneer anomaly, the cosmic alchemy of strange stars, or something else entirely. Let's keep the conversation as boundless as the cosmos itself. The greatest chapters of discovery aren't written yet, and who knows, the next one might start with you.